Hello, in this video we're going to look at the Shapiro Wilk Normality Test, and this is a follow-up video to a video I put out called using our Rankit plots versus QQ plots. And that's a pretty nice video too to explain how each of these plots are calculated. Now the Shapiro-Wilk Normality Test uses rankits in its test statistic, and a rankit is the mean of an order statistic from a standard normal distribution. And so we're talking about order statistics, so we'll need a density. So this is the jth density of an order statistic. And then I created a function to calculate the rankit. So a rankit is the mean of an order statistic from a standard normal distribution. So what this does is it inputs in, which is the sample size. So if I put a 6 there, then it's going to create a vector of 6 where the first component is the mean of the first order statistic, the second component is the mean of the second order statistic, and so forth. And so that's what this function does. So let's load it. Then in the test statistic, the Shapiro-Wilk test statistic, it uses the covariance between these order statistics from your sample. And to use the covariance, you need the variance and you need the covariance, but in that you need the expected or the second moment of the order statistic. So what I do is very similar to the function above. I have the density for the order statistic, and then I integrate it over all possible values from negative infinity to infinity. But here I take x times x, and that's the second moment of the order statistic. So it creates a vector of, say, sample size 6, so a vector of 6, and the first component is the second moment of the first order statistic. The second component is the second moment of the second order statistic, and so forth. Notice when we're calculating the rankits, or the mean of the order statistics, I take x times the density and then integrate it over all possible values, negative infinity to infinity. I think I forgot to show that. Now to calculate the covariance, we need the joint density for the ith and jth order statistic, which is this. And I should have stated earlier that little f is the standard normal density, capital F is the CDF, or cumulative distribution function, for standard normal. And here I create a function called denij, which is the density of the I and j order statistic. So this is really just this function up here coded in R. Now to calculate the covariance, I think it's easiest to calculate the expected value of x times y, because then if you subtract off the mean of x and the mean of y, you get the covariance. And so this is the expected value, so it's a double integral. And remember, and we're going to think of x as being less than y. So we're integrating x from negative infinity to y, and then y goes from in negative infinity to infinity. So here I take x times y times the density function, the ij density function, and then I integrate x from negative infinity to y, and then I integrate y from negative infinity to infinity. So I need to load this function, and now I want to go through an example. But first I want to go to the Wikipedia page of the Shapiro-Wilk test and look at it. And this is it. So it's a test for the normality. So the null hypothesis is that your sample comes from a normal distribution. The alternative is that the sample doesn't come from a normal distribution. But this is the test statistic that we're calculating, W. So there's no known distribution for W. So all the critical values or cutoff values are generated through simulations. And this is it. So note the denominator here is the sum of squares total. So it's like the sample variance without the n divided by n minus 1. The numerator, the x, and then in parentheses I, that's the order statistic, and we go from 1 to n. So we take the first order statistic times a1, and then and then after that sum we square it. But let's look at what the a's represent. The a is this vector here. Now m is a vector when it's down here, and it represents the rankits. So these are the means of the order statistics. So m is the vector of rankits. Now v is the covariance matrix. Of course we have to take the inverse of it. And then c is actually the length of this vector m transpose v inverse, which is this right here. So it's the square root of that. And then once we do this calculation, we get the a vector and we put it back in and we calculate it. Anyway, so this is what we're going to calculate in this example that I'm going to show you. One note before we go is that these are really tough to calculate, and I think that the way that I calculated, I can only calculate rankits up to a sample size of 170, but to calculate this test statistic, I think once I get over 25, then it really slows down. I think the biggest I've done was 27, and I'm like, I don't really want to do bigger than that. So what they did was created approximations for anything bigger than 3. So when you run the Shapiro-Wilk test in R, you have a sample size of 3, it's the exact. It actually calculates this test statistic, right, that you see on the screen there, W. For 4 or more, up to a certain number, and I don't remember that number, it's an approximation. And then once you get past that number, up to 5,000 observations, which is the biggest sample size you can have for the Shapiro-Wilk test, it uses another approximation, because it's really, really tough to calculate this test statistic. And the approximations are very close, and I'll show you what we have in the test. So let me close this window. So let's go through an example of size 6. So our sample size is 6, and we're going to generate 6 random uniform distributions. So it's not normally distributed. That's going to be our data. And then we calculate the rankits, which are the mean of the order statistics. And let's look at that. So it's a vector of size 6. Notice that it's symmetric, that this number is this number. And that makes sense. If you're going to sprinkle 6 observations into the standard normal distribution, those 6 data points should land on the z-scores somewhere sort of evenly, and that's what this represents. The second moment of the order statistics, I create a blank matrix V, which is going to house the covariance matrix. So this for loop, I go use I and j from 1 to n, 1 to n, but I only calculate for I less than j, and then I calculate the expected value, the expected value of x, y, and then I subtract the means of each of those. So that for loop is crunching the covariances, and let's look at it. So it created this, and it missed the variances. Now to calculate the variances, I use the diag v, which it just isolates that diagonal element, and then I take the expected value of x squared minus the expected value of mean quantity squared, and I plug it into that v matrix, and there it is. There's the variance covariance matrix. Now to create the Shapiro-Wilk test, I take the rankit times v inverse, and I'm going to put that in A. And now I calculate the test statistics. So I take A times X, or data, and the length of the vector is below here, which is a constant, so I don't carry it along in that calculation. I just divide it later. And then here is the variance of the sum of squares total. And then I print it and look at it. So for a sample size of 6, the exact Shapiro-Wilk test statistic is not 0.9728, and the approximation is 0.9730. So very close. Let's do this for a sample of size 3 and see what we get. And it's pretty fast, but notice that in R it's 0.78988, and here it's 0.78988, and every time you run this for sample size 3, those two will be exact, because in R they calculate exactly for sample size 3 and then only approximate it for bigger. So let's go to 12 and recalculate it. And notice it's slowing down a little bit. In R, it's 0.96557, and the exact ShapiroWilk test statistic is 0.9656. So it's close to 3, or 4 decimal places. And that's it. That's the ShapiroWilk test. I'm not going to calculate it for more. I'll put this program in the comments if you want to play with it. And really, this is just an informative video on how to calculate the ShapiroWilk test statistic. You should always use the built-in functions for R to do this. But here's some cool properties that I'll probably put out a video soon. That if we calculate that covariance matrix when we have order statistics from a standard normal, the rows of the covariance matrix sum to 1. And notice in R, it's only really close. It's 5 or 6 decimals close. The sum of the rank, it should be 0. And it is. It's really close to 0. There's rounding error in it. And the sum of the second moments vector should sum to the whatever length that vector is. So in this case, it should sum to 12. Yep, and it does. Let's go through these properties just one more time. That's kind of cool. So let's say a sample size of 7. I think we did 6 already. So first let's look at the ShapiroWilk test. So it's 896, 896. I mean, it's really close. And then let's look at these properties again. The rows should sum to 1, and they're really close. The rankage should sum to 0, and again, it's really close. And the sum of the second moments should be 7 this time. Yep, and it's exact. Alright, well, that's all I have for this video. Hopefully you enjoyed it. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.